Ladies and gentlemen, welcome. This is the last part from the first chapter. So in this last part, we will talk about classification of functions and inverse of functions as well. Like I said, this is just the last part from the introductory chapter. This introductory chapter, it's easier than what will follow next. And I would like to start with the classification of functions. So let's start with that. And well, we've been talking about functions, and we have seen with what kind of functions we're dealing with, and so on. Well, now let's classify them. And I would like to start off with the first one, with the polynomial functions. Here, well, when I talk about polynomial functions, I mean the following. A polynomial function is a function of the following form, and probably you already know this. This is f of x is a n x to the power n, right? Plus a sub n minus 1 x to the power n minus 1 plus a1x plus a0. So this is what we call a polynomial function, where okay, let me say it like this, where n is a non-negative integer, and these numbers a naught, a1, an are constants, right? And we call these constants the coefficients of the polynomial function. Anyway, let's just say a few things. If an is non-zero, if this coefficient, if what we will call the dominant coefficient is not zero, the integer n is called the degree, right? We call this the degree of the polynomial. All right. Also, like I said, a sub n, we call this is called the leading coefficient, leading, or we would say dominant coefficient, right? Okay. And this a0 is constant, or sometimes we call this the free coefficient. Anyway, it doesn't really matter. It's just a notation. All right, now let's point out some remarks here. And the first one I would like to say is that a constant function well, has degree 0. As you can imagine, well, this is f of x equals a, right, where a is just a constant, right? All right. A linear function has degree 1. Well, that's, again, these functions look like this. It's ax plus b. And now we keep going. A quadratic function has degree 2. Right? And these functions look like this. So this will look like f of x will look like ax squared plus bx plus c. Now let's keep going. A cubic function. A cubic function has degree 3. Right? And this functions will look like this, is ax cubed plus bx squared plus cx plus d. And now let's do one more. A quartic function will have, as you can imagine, degree 4. Has degree 4. And this functions will look like this. F of x will look like ax to the 4th plus bx cubed plus cx squared plus dx plus e. All right, so these are the functions. Well, these are the polynomial functions. As you can see, we go all the way from degree 0 to degree 4, right? And well, here I would like to say some other things about other functions. So this was the polynomial function. And the second one, well, let's say the rational functions. Let's see how these functions look like. Well, let's say a rational function is the quotient of two polynomial functions, Let's say p of x and q of x, right? P and q. Well, and we will call this f of x, this rational function will be, like I said, p of x over q of x. And of course, this q of x has to be non-zero, right? So we can divide by it. So this is the rational function. These are the rational functions. Now let's see about the exponential function. And we will study this function, these kind of functions, the exponentials and the logarithms. We'll study them later on in the second chapter, sorry, when we'll talk about limits and so on. And we will talk also about the number e, which is the base of the natural log. Anyway, we'll get there. The exponential functions will look like this. Well, I'm just going to say explicitly, they look is f of x. These are the functions given by f of x equals b to the power x, where this guy b is a positive constant, and b is not 1. So these are the exponential functions. They look like this, right? Okay, now let's see, well, in pair with this, and you will see that both of them will be very, very important because they'll be the inverse, one of them is the inverse of the other. Logarithmic function. The logarithmic functions will be given by the following, and will be f of x equals log in base b of x. That's how we read this. And again, b is a positive constant. right? And b is different than 1. Okay, now, and the last class of functions are called the trigonometric functions. And we will talk about these functions. Well, we have seen some of them. We've talked about sine, cosine, tangent, cotangent, secant, cosecant, and so on. So these functions are sine, cosine, tangent, cotangent, secant, and cosecant. And we have defined them previously. We have seen, right, secant is 1 over cosine, cosecant is 1 over sine, tangent is sine over cosine, cotangent is cosine over sine, and so on. So we have studied these functions. We have seen also their values and so on. Okay, now, since we've talked about these functions, and like I said, I will leave the exponential and the logarithmic functions, I will leave them for study later on. I would like to talk about something else, the inverse, trigonometric inverse functions. And we will see that we will talk also about the inverse trigonometric functions as well. All right, so let's see what is the inverse of a function. There will be a method to find these functions. So let's go. So the first thing we need to talk about is the method. So methods of finding the inverse of a function. All right, let's see. So how we find the inverse of a function? Well, for a given function f, we write, let's say, y naught will be the value of f, of the value of x naught through f, to indicate that f maps the number x naught, right? So we want to map these number x naught, which is in its domain, into the corresponding number y naught, which is in its range. So that's what we're doing, right? All right. Now, if f has an inverse, whatever that means, let's call it f, and we'll f to the -1, right? This is how we're gonna denote the inverse of a matrix, or the inverse of a function, right? Well, if f has an inverse, and we'll see under what conditions we do have inverses. So if f has an inverse, call it f to -1, then this is the function that that reverses, let's say, the effect of f, and here I should be more specific, in the sense that that this guy, that we have the following, f inverse evaluated at y naught will give us f of, it will give us x naught, right? And now let's draw a picture so that things will be a little bit clearer. So let me just be here. This is the domain x. And let me say that I have a point here in the domain. And this, let's say this is the range. This is y, which is the range. This is the domain, right? And this point x naught is sent to another point, y naught, in the range. And this is sent through my function f. Well, guess what? If I want to send back that point y naught to the point, to the initial point x naught, what I'm going to do is the following, and I can do that. And this will be sent back through this function, f inverse. That's exactly what this function does. And by the way, I want to make one remark here, which is very important. So I will leave the picture for you to look at. The picture is very important to remember how this inverse function operates. But I would like to point out a remark which is crucial, because I don't want you to mess these two things. The symbol f to the -1 here, like we said for inverse, does not mean one over f. Please, that's not what we mean. It's just a notation for the inverse. And let me give you an example. Again, let's do an example so that things will be even clearer. And let me just let me draw a picture first. Let me look at this domain, and let me look at this range here. And now let me put some numbers here. 2, -1, 5, -9, right? And let me consider that these numbers are sent to the range through this function, f of x equals 2x. So basically, we take elements from the domain. So here's the domain. Here's will be what we will call the range. So in other words, we take elements from the domain. As we can see, we have 2, -1, 5, and -9, and we're going to send them to the range through this function. Basically, we take each element and we multiply them by 2. So we will have 4, we'll have -2, we will have 10, and we will have -18 here. Wow. Well, guess what? If I want to send these back from the range to so if I want to send these back, how are we going to do? Well, the function that will send these, in fact, let me, so if I want to send these back, what we're going to do, we'll do it through this function. F of x is x over 2. And this is what we call the inverse. So that would be the inverse. So this is just an example. I didn't say anything. It's just to give you some kind of an intuition of how to see if a function has inverse, an inverse or not. All right. Now, well, the question is, how do we find the inverse of a? So let's address this question. How do we find the inverse of a function? That is the question. So we would like to address that. Okay, well, let's see what kind of a criteria. So the answer is given by the following, let's say, criteria for the existence of the inverse function. And let's see under what conditions does the inverse well, the story is like this. So we've talked about one-to-one functions, we've talked about untold functions, right? Well, this means that one-to-one and untold means that the function is bijective, therefore is invertible, so we can find the inverse. But let me shorten this a bit. So the inverse function can only be found for one-to-one functions. So we can only deal with, we have to deal with one-to-one functions. That's the only way we can find the the inverse of a function, right? All right. Let's see an example. So I think this is example 2, and this one is example 1, let's say. All right. So let's see an example. And let me take the following function. F of x is x squared. So I'm going to take the simplest quadratic function. Or, right? F of x equals x squared. And as let's say that f is defined on real numbers and real valued function. So let's draw the graph. Okay, and now I'm just gonna draw it like this. Oh, that's a very unfortunate. I'm not very good in drawing things. Okay. Okay, this is not quite symmetric. Just all right. So this is a more or less a parabola, and we have here, let's say, we have 2 points. Let's say x1, and let's say we have here x2. Okay. And here we have y1. Well, if you look at the picture, and we've talked about the horizontal line, so let's look at the picture. So according to the horizontal line, the function is not one-to-one. One-to-one. Well, just note the following. If we look at the domain, well, in our case is R. Again, this is R and R. And if I take these 2 points, x1 and x2, guess what? They're mapped, both of them, into the same point, y1. So let's write this. Notice that both points x1 and x2 are mapped into a single point into y1. Well, unfortunately, at this point, it is not possible to identify the inverse image of y1 uniquely. This is very important. We cannot do this if an inverse function exists. Okay, so the inverse does not exist. So if we have this function, well, the simplest quadratic function, we define it from R to R, we cannot find the inverse, right? So the inverse does not exist. Well, let's see, what kind of method? So method of finding the inverse of a one-to-one function of a one-to-one function. All right. Step one. What we would like to do is to replace f of x by y. Step two, we solve the equation for x in terms of y and now step three, we replace y by x and x by f inverse of y, f inverse of x, sorry. Right? Anyway, or f inverse of y, maybe that would be inverse of y, maybe that would be more accurate, to be honest. All right, let's see an example. Example 3, find the inverse of, and let's take a linear function of the function, well, let's say f defined on R and real value, and f of x is given by 3x plus 5. All right, we have this function and we want to find the inverse of this, right? Okay. Well, clearly this is a one-to-one function. So step one, let's apply the above steps. This is quite easy very straightforward to do. Well, the first one is to replace f of x by y. So we have 3x plus 5 equals y. Now step two, solve the equation for x in terms of y. So we have to solve this for x. Solving for x, we have 3x equals y minus 5, or equivalently, x will be y minus 5 everything over 3, right? So the inverse, now we're going to replace x by f inverse. So the inverse is given by f inverse of y is y minus 5 over 3. So that's the method we use for this. So that's it. This is how we find the inverse of a linear function. It's pretty straightforward. We can do for any linear functions and so on. All right. Now, how do we want to see something graphically about the inverse of a function, and I would like to address the following question. How do we obtain the graph of f inverse, right, when the graph of f exists? That is the question. And there will be this famous, this amazing property of these two functions of f and the inverse of f. Well, we'll do the following. And well, I'm just gonna draw the picture directly so that you can see it. I think that's the best way to do it. And I'm just gonna do it like this. So this will be the graph of f. Actually, no, maybe I want to do it like this. Maybe it should be something like this. Now I'm going to draw something. This famous line, the first bisector it's called, y equals x. So this is the graph of, this is y equals f of x. And now guess what? I'm just going to draw, and let me put here a different color. I'm just going to draw it like this. All right, I hope they're symmetric, but anyway. So this will be this is the graph of y equals the inverse. Let me point it out in this way now. So this is the two graphs. If you look at the picture, they're symmetric towards the first, towards this line, y equals x. And let me just write this in words. Simply reflect the graph of f from the line y equals x. We just reflect it, or if you want, or plot all xy, all these points xy, which are the coordinates of the graph of f as y-x coordinates. So we're just going to interchange the two. So we interchange xy coordinates for each point on the graph. So that's what we're doing. Anyway, so that's the picture you have to remember. They're symmetric towards the first bisector. Now, in the remaining time, I would like to talk about the inverse trigonometric functions just a little bit, and probably we're going to stop here. So the inverse trigonometric functions. And at some point, you will see that we will be talking about, we will meet with these functions again later on when we'll talk about derivatives or even limits, in fact. And the first one I would like to talk about is the inverse sine function. The inverse sine function, right, it will look like this. In fact, y equals sine to the -1. This will be the inverse, in fact, or you can also look denote this by arc sine of x, right? So this is, and let me say that y equals sine of x, sine to the -1 of x, so that's the inverse, right? If and only if x is sine of y, right? This is, and we're going to restrict this function so that we can find the inverse for y between -pi/2 and pi/2. On this closed interval, right? Okay, right? All right, and now the second function I'd like to talk about is the inverse tangent function. Which is in the, we'll write this as tangent, y equals tangent to the -1. So this is the inverse, or you can also write this arc tangent of x. Either way. And again, y equals the tangent inverse if and only if x equals tangent of y. Well, and here we have a restriction as well for y. It's between -pi/2 and pi/2. Okay. And now let's define the other trigonometric functions, and let's see, in fact, let's draw the following chart. So definition of inverse trigonometric functions. We're going to draw the following chart. So let's put here inverse function. Let's put here the domain of the definition. And here we'll put the range. All right. So we're going to draw this chart. All right, let's see. Let's take the first one, y, the arc sine of x, so the inverse of sine. Well, the domain, where this is defined, we know that sine has, the range is -1, 1, so the domain will be -1, 1. And we want to restrict this so that we can have an inverse, so we want to restrict this to -pi/2 and pi/2. So this will be the quadrants 1 and 4. One and 4. All right, let's see the second one. We'll take we'll take cosine inverse. Again, the same thing will happen here. This will be, the domain will be -1, 1. All the values x for which, well, okay, let me put here x is in this interval. And the range will be 0, y will be between 0 and pi. So this will be quadrants 1 and 2. Now let's take y is the tangent inverse of x. Right? Well, this will be, x will be between negative infinity, infinity. And the values of y will be negative pi over 2 and pi over 2. And this will be again quadrants 1 and 4. Okay, now let's take y to be cosecant inverse. Well, in this case, we will have, well, either x is greater or equal than 1, or x is less or equal than negative 1. And the values will be, again, negative pi over 2 and pi over 2. Of course, y has to avoid the value 0. Again, these will be quadrants 1 and 4. So the same goes here. And now let's see another one. Y equals secant inverse of x. Well, again, x is greater or equal than 1, or x is less or equal than 1. And now we have quadrants 1 and 2. So y will be between 0 and pi. And it will avoid these value, pi over 2. So this will be quadrants 1 and 2. And the last one, y equals cotangent inverse. This will be x is between negative infinity and infinity. And y will be between 0 and pi. So quadrants 1 and 2. And, oh, right? So this is the chart of the range and of the domain and the range of the inverse trigonometric functions. So we'll see that this is for where the function, the inverse actually exists. So we need to be careful with the range. And now let me just give you some formulas for the inverse functions. For example, if we apply sine inverse of x, this will be nothing other than just x. This will be the identity function. So this happens for all x between negative 1 and 1. Well, another one, if we want the other way around, sine inverse of sine of y, guess what? It will be the same thing for all y between negative pi over 2 and pi over 2. And the same thing happens with the tangent. So tangent of the tangent inverse of the arctangent of x will be x. This happens for all real x. And if we want the other way around, if you want to see what tangent inverse of tangent of x of y is, this will be y for this time for y, all values of y between negative pi over 2 and pi over 2. All right, so these are the formulas. You can see if you compose, basically, that's what we're doing here. If we compose the function sine with the inverse of sine, it will give you the identity. So that's it. Well, I think this sums up everything for this chapter. This is an introductory chapter. I would like to emphasize that. So you must know everything that's going on here, because next time we will start talking about limits, continuity, and these properties of functions will come into play. So this is just a warm-up for the rest of the material. Okay, thank you very much. So I guess I'll see you next week. I'll give you some material in advance to read about the next chapter, and then there'll be videos where we'll talk about the material. Okay, thank you.